All right, folks, welcome back. So last time we did a little bit of business with orthogonal complements, and now I'm going to show you why we went through all that trouble to define something that was perhaps a little bit abstract for us, something that's not the most intuitive thing to work with in practice, but it's actually going to be really, really interesting for us in the following sense. That we are going to be able to describe the four fundamental matrix subspaces through this idea of orthogonal complements. And let me kind of give you a rundown, I'll give you an example of how you might, or why you might expect that to be the case. So let's go ahead and recall from chapter 2 that we have the following matrix, right? And this guy I'm going to go ahead and throw into let's see, I'm going to throw this into MATLAB Mobile real quick. Come on, where's the matrix? Where's A? There he is. Go back down one. Awesome. Okay, so A here is the matrix in that example. You can double check, right? 1, minus 3, 2, 0 across the top. Yep, minus 5, 1, minus 1, 5, 1, 1. Yep, and then 2, minus 8, 1, minus 1. Oh, yay, great, awesome. So this is the matrix from the notes. And what I want to point out here is that this guy is going to have a null space. And we could have seen that just by saying, okay, there are 4 columns in this matrix and the columns are only 3-dimensional vectors. So that means that I have more elements than I have dimension in R3. So I definitely have a non-trivial kernel for this matrix, and I can actually compute for this guy, let's call this Q. I can get an orthonormal basis for this kernel, right? And you can double check Q transpose star Q is indeed the identity matrix, at least numerically approximate. Okay, so we have a basis for the kernel here. And more to the point, the question that we want to answer is, when does this guy have a solution? When does AX equals B have a solution? I'm just going to go ahead and take some arbitrary vector here, some 3x1 of 1s, and I'm going to ask, does this guy have a solution? Did I do that right? Oh, it's got to be a 4. Is that right? No. /B, not /. Shame on me. There we go. So rank 2 deficient, or rank deficient, rank is 2. So MATLAB is going to spit out something here. It's going to tell me that you can go ahead and use this vector. And I'm going to go ahead and say that x is a/b. But this is supposed to be the vector that if I multiply a into, that I should get the b vector, and that is not the case, right? A star x is close, but it's not equal to the b vector. So / is actually doing something under the hood, and we'll explain this one in chapter 5 of exactly what's happening. And in fact, we'll actually see a little bit of this in the next video of what is actually happening here. But the point is that b, if I were to row reduce this, so RREF of A with B, that guy creates an inconsistent matrix. That means that B is not in the image of this matrix. Okay. So wouldn't it be nice if there was a way for me to figure out if this system had a solution before I go through all this trouble of potentially saying that I have a solution when I definitely don't? Well, sure, actually, you can do this in general, right? If I were to set up an augmented system here, right, this A against B, then what's going to wind up happening is in order to make this, in order to row reduce this guy completely, there's going to be, let's see, this is row equivalent to, what did we see? Right, in general, so the pivots are in the first 2 columns. So I get a 1, and then a whole bunch of stars. There we go, and then 0, 0, 0, 0 in that last row. And you will find that there is this relation in the last column, or in the solution side column. And in order for this system ax equals b to have a solution, we need to zero out that final component. That minus a plus b minus c has to be 0. And this is exactly the condition that we are looking for, that b, if it's given as the vector abc, this vector is in the image of a, right? Ax equals b has a solution, if and only if we can zero out that last entry and make the row-reduced matrix consistent, or make the system consistent. So what we're going to do here is observe that I can go ahead and compute the co-kernel of this matrix. So why the co-kernel? Well, I'm glad you asked, dear student. Let me show you what it does in the first place. So notice that the co-kernel I can compute as the null space of A transpose. And notice the coefficients here. Actually kind of interesting that they go in that order. Did I write it down correctly? Interesting. I want the co-kernel, so it's the kernel of A transpose. Yeah. Interesting. Did I do this right? Yeah, pretty sure. So A transpose is that guy, and if I were to RREF A transpose, yep, I'll get something like that. Yeah, interesting. Okay, but either way, the null space here you can compute. We'll go ahead and give you some vector here, and I'm not entirely sure what went wrong with the calculation, but I'm going to skip it for the moment because my notes are still valid with or without that being correct. The idea is that if I look at the co-kernel, notice that this span here, right, the span of this vector is actually the orthogonal complement, or sorry, that B, if I'm going to be in the image, has to be in the orthogonal complement of that space. Kind of strange here, right? There's no coincidence, right, that B here actually is in the co-kernel. It's not in the co-kernel, it is that right? B is in the co-kernel. Oh my goodness. Okay. B would have to be in the image of A, and it turns out that this guy will be the orthogonal complement of the co-kernel. So if I can show that B is orthogonal to every element in a basis of the co-kernel of a matrix, then I've already satisfied this compatibility condition, this minus a plus b minus c equals 0. All right, so let's see where we can go from here. If there's some generality that I can make, some formal statement that I can propose to make this rigorous, and we're going to do that here. Now the theorem is that the kernel of a matrix is actually the orthogonal complement of the co-image of that matrix, and more importantly to us, that the image of the matrix is exactly equal to the orthogonal complement of the co-kernel. So this is exactly the condition that what we're going to be using to show that a matrix, or that a system AX equals B is solvable, and it's using this fact here that we're going to appeal to orthogonality rather than Gaussian elimination to make that judgment call for us, right? Computing orthogonality is much quicker than actually solving a system and then realizing, well, crap, it doesn't have a solution, or row reducing and finding there's no solution. So to see this, right, we're going to kind of buzz through the theorem, the proof very qualitatively, but it is in your textbook. You can consult at a much more leisurely pace if you'd like. But if a vector belongs to the kernel, right, we're going to show that if a vector x belongs to the kernel, then it actually belongs to the orthogonal complement of the co-image, right? And then vice versa will show that if something belongs to the co-image, the orthogonal complement of the co-image, then it's really going to belong to the kernel of A as well. So these two sets contain one another. Therefore, they have to be the same. So X belongs to the kernel is the same thing as saying that AX equals 0. Okay? So the way that we're going to interpret this is through how we compute the matrix multiplication A times X in the first place. If we look at A as having a whole bunch of vectors, a whole bunch of row vectors, A1, A2, all the way down to AM, and we multiply that into X, then what's really happening here is I get a whole bunch of dot products, right? I get A1X, I get A2X, oh, not X2, just X, and all the way down to AMX, or dot X. Okay, so this is the matrix multiplication on the left-hand side is just a collection of dot products. And if we're saying that this A times X is equal to 0, that means that every single one of these dot products on the A times X side has to be 0, right? All these vectors are orthogonal to X. Okay, so what we wind up with a little bit further down the road here is that means that each column, not of A, but of A transpose, must be orthogonal to the vector X. So that means that X itself is going to have to be perpendicular to the co-image, right? The image, remember, is going to be the column space of some matrix, and co just means put A transpose in front of it. So this is the image of A transpose, right? And A transpose, the columns of A transpose are the rows of A, and that's exactly the computation we just made here up at the top. And very similarly, each column of A transpose must be orthogonal to X, so that any element of the co-image is also orthogonal to X. Right, so there's the backwards containment as well. Right, if you are orthogonal, that means that, if you are orthogonal to X, that means that if A transpose is equal to A1, all the way down to AM, then then each of these columns, A1 dotted with X, A2 dotted with X, all the way down to AM dotted with X, all of these are 0, and this is exactly the computation that we did upstairs, but now we kind of think of it in terms of A rather than A transpose. So instead of the columns of A transpose, we're looking at the rows of A. And this gives us the equality that we need, that this collection of dot products must be 0. Right? And we can show in a very similar sense, you can start with A transpose instead of A, and you will get the resulting statement for the co-kernel. And the way that it would actually turn out is that the co-kernel of A would actually be the orthogonal complement of the image of A. Okay? So this is the relationship that we get between the 4 fundamental subspaces when we think about this this matrix as being a linear map on inner product spaces. So we can actually see the main point of the theorem is that we know exactly when we get a solution to this. The only time that we get a solution to AX equals B is if B is in the image of A. And the theorem we just showed is that this is the co-kernel, or the orthogonal complement of the co-kernel. So that means the only time that we get a solution to AX equals B is if B is perpendicular to the co-kernel of the matrix. And that is a condition that is more easily verified than actually row reducing the matrix AX equals B in the first place. So let's see this in action. Right, so solving this, right, back to MATLAB Mobile. I will go ahead and create a new matrix A, and that was going back here, it is 1, 2, 3, 2, 2, 3. Okay, so transpose 1, 2, 3, 2, 2, 3. Transpose, there we go. And I would like to create the vector b, which is from the notes 0 by 1 by 0. No problem. I'm pretty sure that's what I had. Yep. So let's compute, right? If I'm looking at the co-kernel here, so I'm looking at the null space of A transpose. Okay. So this guy, this is a basis for the co-kernel of the matrix. And this guy, if I am to believe my theorem that the co-kernel is exactly the orthogonal complement of the image, right? I'm looking at this statement up here, that this guy should row reduce to a whole bunch of vectors that are perpendicular to the thing that I just computed. So RREF of A, let's see, RREF, this is a basis for the image, and I get the co-kernel off of this. Yeah, the co-kernel. Oh, sorry, no, that's not what I'm doing. That is not what I'm doing. I'm checking this against the B vector, right? So B has to be perpendicular to every element of the co-kernel, so null. If I were to dot, so B transpose times null of A transpose. Interesting. What is going on there? So 1, 2, 2, 2, 3, 3. Did I write it down correctly then? A is 1, 2, 2, 2, 3, 3. Yeah, 1, 2, 2, 2, 3, 3. B is 0 by 1 by 0. And we can compute that the kernel, right? The co-kernel, yep, so the co-kernel is the null space of A transpose. And this is exactly what we wind up seeing on the lecture notes, just in orthonormal form. Okay. So notice, oh no, that's fine, that's right, that's what's supposed to happen. Right, so notice that this computation, right, the vector B up at the top here is not perpendicular to the co-kernel, or it's not in or it's not perpendicular to the co-kernel. And the Fredholm alternative then, right, that theorem at the top, right, this theorem saying when we have solutions to AX equals B, has a solution if and only if B is perpendicular to the co-kernel. And the co-kernel is spanned by a single vector, so I can check the dot product. If I go back to MATLAB Mobile, I can do that. B transpose times this, or you can just do dot, I believe, B with the answer vector. And that is not 0. Therefore, AX equals B. So if I wanted to solve this, A backslash B, it's going to give me something, but it's not going to mean anything because A star X, oh, A star little x, oh, for crying out loud, A star little x, this is not equal to the B vector. It's close in some sense, but it's not equal to the B vector, so this system actually doesn't have a solution. All right. And more generally, if we were to figure out which vectors were solvable, right, or which vectors AX equals B had a solution for, we are checking a compatibility condition just like we did in the previous example, or in an earlier example, that this guy has a solution if and only if this solution vector ABC is perpendicular to a basis for the co-kernel. And that would mean that A is irrelevant, but B and C have to be in opposite proportions. So I'll say twice B, or twice C. No, yeah, we'll do B and then 3 times B. Negative 3B. And those guys, no, it'll be plus 3B. That would be a complete set of solutions. right? And this would mean I would have a basis for my image that looks like this. All right. But anyway, the boxed equation is the takeaway here, that you can compute this compatibility condition more readily than you can actually solve an AX equals B dense or a dense matrix computation or Gaussian elimination. Now, for a bigger system now, right? We can actually check this. So I'm going to go ahead and append one row here. So A equals A transpose. Do I want that? No, A is equal to A, but I'm going to add the row 4, 4 to it. And voila, there it is. And let's see. I'm looking to figure out what is the compatibility condition that I need in order to guarantee that this system has a solution. Well, I'm going to go to the co-kernel. So I'm going to ask, what is, and I'll do this, Q equals the null space of A transpose, right? Null space of A transpose is the null space, is the co-kernel. And there we go. We have 2 dimensions now to deal with. So I need to make sure that my solution vector B is perpendicular to both of these vectors in the basis. All right. So let's see, if I wanted B equal to the vector of ones, not eins, ones. Okay, so B is this. And I check what is the dot product of B with each of the vectors in Q. Well, turns out that is definitely not a solution because it's not perpendicular to either of those vectors. Okay, so that would mean that AX equals B doesn't have a solution. So let's verify that. A is, or X equals A backslash B, and that A star X, yeah, it's definitely not equal to B. Okay, A star X actually is, again, kind of close in some sense. Those components are near 1, but there is no solution to AX equals B because B is not in the co-kernel of A, or it's not perpendicular to the co-kernel of A. And that's exactly what this work is doing. So by hand, you would go ahead and compute, you would compute by hand this collection of basis vectors and simply dot the ABCD vector against each of them to get this set of conditions that you need to satisfy in order for your system to have a solution. And we can just kind of come up with one off the cuff here. Satisfying the first equation, right? So if I make sure I direct your attention to the right spot, I can go ahead and effectively ignore the A in this case. So A can be 1. B and C here, let's see, B and C have to be in 2/3 ratio. So B would be a 2, say, and C would be a 3. Yeah, that would work. And then D has to be twice B, which would be a 4. So I'm proposing that 1, 2, 3, 4, of course it is. I'm proposing that the vector 1, 2, 3, 4 is actually a solution to this system, and you can actually see exactly what it is, right? You're going to get the x vector is 1 by 0 for this solution. But you know what, for posterity's sake, throw it into MATLAB. And we verify B equals 1 by 2 by 3 by 4. And we ask, is B perpendicular to each element of the co-kernel? Yes, indeed. And we check. X is equal to A backslash B. And exactly like I said, right? We're going to get A times X is equal to B. Yeah, and it's going to come up to a numerical accuracy issue. You can actually see it if I increase the precision in the computation. A star X. Oh, geez, did it again. A star X. There's a whole bunch of zeros here. Can I do long format double? Okay. That was just a check. But the point is that this is very, very close. right? It may not be exact within the machine epsilon in this case, which is basically 10 to the minus 16. So I'm going to have to go way down in precision. I'm going to have to go way up in precision to see where it goes wrong. But a star x and b are effectively the same vector in the computer's eyes. So that is good enough for me. And we come back here. That's exactly what we were showing. Is that 1, 2, 3, 4 is perpendicular to the co-kernel, and therefore ax equals b has a solution. And that is what the Fredholm alternative is, right? And I think that's where I want to stop this. Is that right? Yeah, we're gonna go ahead. Yeah, we're gonna go ahead and stop the video at this point. But the big takeaway is this theorem here in the box. Whee! Right, this is a big deal for the study of differential equations, in particular for non-homogeneous differential equations. We want to figure out how to solve these guys, or figure out when they have a solution, so that we don't run on a fool's errand to go looking for something that doesn't exist. Okay? And checking this compatibility condition or collection of compatibility conditions is a lot simpler than actually trying to solve these equations directly, because they do take a long time just to run through one algorithm. Sometimes on the order of hours, sometimes even on the order of days to run through your computation. So you want to make sure you're damn certain that the solution exists before you go hunting for it. And this is an easier condition to check than actually solving something directly. And we're going to go ahead and cut the video here. I'll show you exactly what was happening in this case. If I go back to MATLAB real quick, we had so if I solved A against the ones vector, we saw that this answer, A star answer, was close, but not quite equal to the ones vector as we want it to be. So what is MATLAB doing in this backslash function?